Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. We find my pen first. Today's topic is the photoelectric effect. So let me write my topic. Our topic is the photoelectric effect. Now, what is photoelectric effect? Now, in photoelectric effect, what we do, we have some metal surface, some metal. Now, on this metal, what we do, we shine some light. Now, this light can be visible light, it can be some other form of electromagnetic radiation. Now, this radiation, this light has certain frequency nu. Now, it's if its frequency is large enough, then what happens? The electrons are ejected out of this metal surface. I repeat, we have a metal. Now we shine light of some frequency nu on it. Now, if the frequency of the light is sufficient enough, this light interacts with the electrons in the metal surface, and the electrons come out of the metal surface. Now, this phenomenon is called the photoelectric effect, and these ejected electrons, sometimes we call them photoelectrons. They are just electrons. Now they are ejected due to the interaction with light. We call them photoelectrons. Now, this photoelectric effect can be uh, explained if we first study it experimentally and then we find the results which we have to discuss. The experimental findings in this photoelectric effect cannot be explained if we assume light as an electromagnetic wave. So if we say wave, nature of light cannot explain the photoelectric effect. We have to discuss that. What is the issue or what are the issues in the photoelectric effect when we try to explain the experimental findings using wave nature of light? Then we will understand those issues and talk of Einstein's explanation of photoelectric effect, in which we uh, assume or take light as a stream of energy bundles called photons. And we will come to know that photoelectric effect can be explained only when light is assumed as a stream of particles, localized energy bundles called photons. So, photoelectric effect confirms the particle nature of light. It confirms the particle nature of light. We know light has a dual character. In under most circumstances, it behaves like a wave, but under certain circumstances, one such circumstance is the photoelectric effect, which is fundamentally interaction between light and matter. Now, in this particular effect, light behaves as a particle. Now, what is the apparatus or experimental setup in which we uh, explain or experimentally study the photoelectric effect? Let me draw that. I will use some other color. Let me use green. So, experimental setup for studying photoelectric effect is like this. Experimental setup for studying the photoelectric effect. Let me draw the figure. If I will draw the figure, you can draw it with me. Then I will explain the setup. Complete this experimental setup. We'll move forward. We have this is a vacuum tube. In the vacuum tube, we have two electrodes. Now, one electrode, left one, is emitter, right one is collector. So E is emitter, C is collector. The emitter is the electrode at which photoelectric effect will take place. So it will emit electrons, and the electrode named as collector will collect the electrons. So emits electrons, here I write collects electrons, right? And what we do, let me complete using the color. Now what we do, we shine light on emitter. Right here, incident light. It has certain frequency, you know that. Now this window is made of quartz. This incident light goes through it. It is quartz window, and inside this tube there is vacuum. So vacuum tube. Now here we connect current meter, ammeter, and then we connect here the voltmeter. Then we have a sliding contact. We complete the figure first. Let me use this color back. The situation is like this. This is simply a potentiometer. This is positive, this negative, and here this is this way. Negative, positive, negative, positive. On this side, this is positive, negative, positive, negative. This is positive side, this is negative side. Now let me use this color. It's connected this way. So this is my experimental setup. Let me write here sliding contact. Now first understand it, then we will move forward. We are externally applying potential difference using this potentiometer setup, and we can adjust that voltage by this sliding contact, right? And that externally applied voltage which we are applying across the two electrodes, emitter and collector, can be measured using this voltmeter. So this is voltmeter, right? Now when photoelectric effect takes place at the emitter, electrons are emitted, and when they reach the collector, in the external circuit there will be flow of current. And you know conventional current has the direction opposite to the direction of negative charge. Now the direction of flow of electrons is this way from emitter to collector, but the conventional current will flow in opposite sense. That current which flows in the external circuit I will be measured by this ammeter. So this ammeter measures, I name it, it is ammeter, and I is my, we call this current as photoelectric current. So this is the experimental setup used to study the photoelectric. We have two electrodes, emitter and collector. They are placed in the vacuum tube. Light is uh, made incident on the emitter if its frequency is sufficient enough. Photoelectric effect takes place at the emitter, electrons are ejected, they reach collector, and if they reach the collector in the external circuit, there will be flow of current. That current will be read by the ammeter, and that current, conventional current, will be in this sense opposite to that flow of direction of flow of negative charge, and this voltmeter will measure the potential difference established between the emitter and collector using this potentiometer set. Now what are the experimental findings? First you need to understand one thing: emitter and collector are almost always made of different materials. When two materials are of different types, there is a hidden potential difference between them. We call that contact potential difference. Contact potential difference. So when electron leaves emitter and it is moving towards collector, it will see two voltages. One voltage is because the different nature of emitter and collector, and second voltage is due to the voltage which is externally supplied by the potentiometer setup. So if V is the net voltage or potential difference experienced by the electrons as they move between emitter and collector, it will be algebraic sum of two voltages. V external voltage which is externally supplied by the potentiometer setup and measured by the voltmeter, and the contact potential difference. Now we assume that this contact potential difference has been taken care of and we express all our results in terms of the net potential difference seen by the electron, which is V. Right? Now, what are the experimental findings? Let us move to that. Let me draw this figure, then we'll move forward. In this figure, what we do, we plot the I, which is photoelectric current. And on this side, we plot the potential difference V. Let this be, use another color here. Let this be my zero value of the potential difference. And on this side, let this voltage be positive. I will explain what that means. Let this be negative. So let me call curve A. Let me get some other color first. This I draw this line at the zero value of the voltage. Then let me draw another curve. I call it curve B. Now understand this. Zero voltage means there is no voltage between the emitter and collector, right? You understand it first. There are three situations. One is when there is no voltage, potential difference, or voltage between the emitter and collector. Second is when emitter is connected to negative, as in the figure, and collector is connected to positive. In that situation, what happens? When collector is connected to positive terminal of the battery and emitter is connected to negative terminal of the battery, that potential difference will help electrons to move from emitter to collector. How? When emitter is negatively charged and electron is ejected, that negative charge will push electron towards collector. And when collector is positively charged, that positive charge will pull electrons towards emitter. That is the situation in this. Now I will write here from 0 to this positive zone, this voltage is helping electrons, helping electrons. In this zone, emitter is connected with negative and collector is connected with positive. So the voltage is helping electrons in moving from emitter to collector. Now in this zone we are reversing the connection, which is not shown in the figure. In the left zone of the graph, that means in the negative voltage, what we do, we connect emitter to positive and collector to negative. When emitter is connected to positive terminal, that positive will not leave electrons. So electrons have to overcome that pull from the positive charge of the emitter if they have to reach the collector. And when collector is connected with negative, that negative will push electrons back towards emitter. So they have to overcome the pull of emitter and overcome the push of collector to reach to the collector. That means when connections are reversed in this circuit, emitter is connected to positive and collector to negative, the electrons have to overcome the opposition. So this potential difference is opposing their motion from emitter to collector. That is the left zone of this graph. So in the left zone, This voltage is not helping electrons, it is opposing electrons. Opposing electrons. At this zero voltage, there is no opposition and no help by the voltage. Electrons are on their own. They have no help or no opposition due to the voltage, right? So, in these curves, what we have done, we have selected some light with certain frequency. Now, frequency is sufficient enough to cause the photoelectric effect. Now, when photoelectric effect is taking place in curve A, there is some intensity of light. So, light has certain intensity I, right? And certain frequency nu, right? In curve B, what we do, we double intensity as in curve A. That is here intensity is 2I, but frequency is nu, right? So we take a light, it has certain frequency, and that frequency is sufficient to cause photoelectric effect in the emitter. Now it is impinged on the emitter, electrons move from emitter to collector. Then we first increase voltage on help zone, in help zone. Then we reverse the connections, increase voltage on that side, and plot the resulting photoelectric current versus this potential difference. In curve B, what we do, we double the intensity, we make intensity twice as curve A, but we keep frequency fixed as nu. So what is the observation? Let us first talk of curve A. The observation in curve A is when there is no help or no opposition at point voltage 0, still there is some photoelectric current. And when help is increased, that means when this positive voltage is increased in curve A, the photoelectric current increases, and then saturates, right? And when we go to the left side, that means when we reverse the connections, when we are now applying voltage which is opposing the electrons, as we increase that opposition, there is a point, there is a reverse voltage or negative voltage at which photoelectric current becomes zero. Now, this reverse voltage is denoted as V naught. It is called stopping potential. It is called stopping potential, right? Now, this behavior of this curve can be easily understood. When photoelectric effect takes place at the emitter, the electrons which come out of the metal surface, they come out with different speeds and different kinetic energies. Some are moving faster, some are moving at slow speeds. So there is a range of speeds in the emitted photoelectrons and range of kinetic energies in these emitted electrons. Now, at zero voltage, some electrons reach the collector and we get this much photoelectric current. But when we increase the potential difference in this positive side, that means when we help them to move, more electrons reach the collector, and when the current gets saturated, that means all the emitted photoelectrons reach the current, they reach the collector, and the current becomes maximum. On this side, what happens? When we move to this larger and larger negative voltage, current is dropping out. That means this current is contributed by those electrons which are the faster in the lot, because only the faster ones can overcome the opposition. So the at stopping potential, the fastest cannot move away because the opposition is that much strong that the kinetic energy for these electrons is not sufficient to make the trip from emitter to the collector. I hope you got it. So as you move towards this negative side where there is opposing voltage for motion of electrons, the current is due to faster electrons, then even the fastest cannot move at stopping potential. This stopping potential is that reverse voltage, that negative voltage, that minimum negative voltage or minimum stopping this reverse voltage at which the photoelectric current drops to zero. Right now, in curve B, we have kept the frequency fixed, but what we do, we double the intensity. We see this height from this point to zero horizontal line is double. So when we double the intensity, the saturation photoelectric current doubles. But for curve B, you can see the behavior is same. That at zero voltage there is some current. So explanation is same. But the important point is in curve B, we have the same stopping potential. So what are the conclusions from this graph? One conclusion, let me list them. Conclusions or experimental findings. First is the photoelectric current, or I should write saturation, the value of the photoelectric current at the saturation situation. The saturation photoelectric current, photoelectric current is proportional proportional to the intensity of light. This is one experimental finding in this photoelectric effect. The saturation photoelectric current is proportional to the intensity of light. Because when you double the intensity of light, it is understood that frequency is kept fixed. The photoelectric current, saturation photoelectric current doubles. This height is double than this height, right? Second conclusion, I name that B is this stopping potential. Stopping potential V naught is independent of the intensity of light. The second thing, the stopping potential is independent of the intensity of light because in curve B you have changed the intensity of light, but for curve B there is same stopping potential as that of curve A. That means changing intensity of the light is not going to affect the stopping potential, right? Now let us talk about the kinetic energy. First, I will tell you an equation. You must be knowing if there is charge Q, if it moves between 2 points having potential difference delta V, then its motion will lead change in potential energy of the system, which is delta U, which is Q times delta V. I repeat, if there are 2 points, points A and B, there is delta V potential difference between them, and it is understood that potential difference will be created by some source charge which will create the field between points A and B. Now if some charge Q moves between A and B, that can move along any path, some charge Q moves, charge Q moves, that can be positive, that can be negative. I am showing here positive. What will happen? the potential energy of the system. Potential energy of the system means the potential energy of this charge which is moving plus the potential energy of the whole system of the charges or single charge which is creating the potential difference. My system is the charges which are creating the potential difference plus the charge which is moving. Now its motion will change the potential energy of the system by amount delta U, which is Q delta V. Now, if this charge Q is positive and potential difference is positive, then change in potential energy will be positive, then potential energy will increase. Now, if charge is positive, potential difference is negative, then product is negative, potential energy will decrease. And similarly, you can check for the other possibilities. Now, point is, if the potential energy decreases, what will happen? Kinetic energy of this charge Q will increase because the mechanical energy is constant, kinetic plus potential, right? So, if the potential energy decreases by some amount, kinetic energy will increase by same amount if the charge begins from rest. If charge begins from rest, then this decrease in potential energy will be increase in kinetic energy. You can understand it from this point also. You know, if there is, if this is earth and it is some stone, if this stone is dropped from certain height edge, what happens to the potential energy of the system? If it goes down, potential energy of the system decreases, but that leads to increase in kinetic energy of this mass. If mass is thrown in upward direction, what happens to potential energy of the mass Earth system? Uh, Earth is having some mass. It is a two-particle system. Now, if you throw this mass in upward direction, its potential energy of the system will increase, but the kinetic energy of this mass is going to decrease. Somewhere it will stop at some point. Same situation with charges. Here, charge is moving in the electrostatic field produced by some other charges. In this situation, this mass m stone is moving in the gravitational field produced by Earth. So, here the force is electrostatic. Here, the force is gravitational in nature, it is just gravity. So, here potential energy will be gravitational one, here potential energy will be electrostatic. But idea is the same. Now, when I drop this mass, Earth is helping the motion. So you can understand this with this zone, positive potential difference. Electron leaves, then this voltage is helping him, helping the electron to reach to the collector. And in negative voltage, there is opposition. That is similar to this situation. If mass is thrown in upward direction, then this gravity is opposing it. Now, one thing you need to understand here. If I throw this mass, if I throw this mass in this gravitational field with some kinetic energy Ke, and it reaches some point where it becomes stationary. When its speed is zero, that means its kinetic energy is zero, then it comes down. Now, here at this point, let it be h height above from the point where we throw it in upward direction, it has attained certain potential energy. Now that potential energy will be equal to kinetic energy at the bottom because it is mechanical energy is conserved. When you throw it some kinetic energy, that kinetic energy comes down, 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 down. Ultimately, that becomes zero, and potential energy increases in the process. At the moment when it stops, the potential energy is equal to kinetic energy at the bottom point. Now let us translate this thing in our case. I will change first the color. Let us translate in here. See, In this negative zone, what is happening? We're increasing the opposition. And we know the current is due to the fastest moving electrons. That means at stopping potential, it is the fastest moving electron which is stopping, just like that stone, right? So its kinetic energy at the start must be equal to potential energy at the moment of stop. That means if Kmax is the maximum kinetic energy, that means the kinetic energy of the fastest electron ejected from the emitter, this Kmax must be equal to EV naught. Understand this. Change in potential energy is equal charge times potential difference. Now my potential difference is stopping potential. E is the charge on electron. So Q is E, charge on electron. And since I told you mechanical energy is conserved, so the kinetic energy here will become potential energy here. Same is the situation here. At the stopping potential, the maximum kinetic energy electron is stopped by the applied potential difference, and the applied potential difference is V naught. Therefore, potential energy must be equal to kinetic energy at the start. That is, Kmax must be equal to EV naught. I hope you got this relation. Now understand this. We said the saturation photoelectric current is proportional to the intensity of light. It is one experimental finding. Then the stopping potential is independent of the intensity of light. It is second. Now, stopping potential itself is proportional to kinetic energy. So, what is true for stopping potential is also true for kinetic energy. Therefore, I can write this conclusion as well. Conclusion C from this relation that the kinetic energy of the photoelectrons photoelectrons is independent of the intensity of light, right? The kinetic energy of the electrons is independent of the intensity of light. These are, there is one more, there is more to it, but we will do that in next class because it may bore you. So let me, before stopping, summarize my lecture. First, I told you that the photoelectric effect is the interaction between matter and radiation, in which we shine light of some frequency at a metal surface. If its frequency is sufficient enough, electrons are ejected. This phenomenon is called photoelectric effect. Ejected photoelectrons are called photoelectrons. Then I told you wave nature of light cannot explain the experimental findings or the results of photoelectric effect, which we have to discuss. So wave theory fails in explaining photoelectric effect. Then Albert Einstein gave the explanation of photoelectric effect in terms of the particle nature of light. He told us that in this situation you have to consider light as a stream of energy packets, localized energy bundles called photons, and gave Einstein's photoelectric equation, which we have to discuss in coming lectures. Then we talked about the experimental setup for studying this photoelectric effect. We said we have a vacuum tube in which we have two electrodes, emitter and collector. Light is made incident on emitter. If it is frequency sufficient enough, then photoelectric effect will take place. Those electrons will reach collector. In the external circuit, there will be flow of current which will be measured by the ammeter, and the voltage which we apply externally will be applied, which we measured by this voltmeter. And I told you emitter and collector are made of different materials. So there is one more potential difference which electron sees as it moves from emitter to collector. So the overall voltage which electron sees in its motion, in its journey from emitter to collector, is the algebraic sum of external voltage and contact potential difference. Then I told you what we do. We take some light here, it has some frequency at which photoelectric effect takes place. It has certain intensity. We graph photoelectric current versus potential difference. We see it saturates at a certain positive voltage. And we notice it that at zero voltage there is still some current, and when we reverse the voltage, that means when we oppose the motion of electrons, there is a minimum value of the voltage at which the photoelectric current becomes zero. That is called stopping potential. If we double the intensity, keep frequency fixed, there is no change in the stopping potential, but the saturation photoelectric current doubles. Then we established this relation Kmax is EV naught, where E is charge on the electron, V naught is stopping potential, and Kmax is the maximum kinetic energy in the lot. That means the kinetic energy of the fastest moving electrons which are ejected from the emitter. So we concluded these results, these experimental findings. The saturation photoelectric current is proportional to the intensity of light. The stopping potential is independent of the intensity of light. And since kinetic energy is proportional to stopping potential, the kinetic energy of the photoelectrons is independent of the light. To keep these things in mind, we will in next lecture discuss other details. So don't forget to like, share, and subscribe my channel. Thank you. Assalamu alaikum.